Is it visible?
Yes, sir.
Okay. So again, there are question answers that here. So first, some questions will be on the historical aspects of vaporizers. Can you guess what is being done here?
Drop method, sir.
Open drop anesthesia. Very good. What are the names of the equipments used to anesthetize?
Schimmelbusch mask.
Schimmelbusch
mask.
Mask. Very good. What is the bottle he is holding called?
Ether.
Ether.
Ether. It is a drug that is there. But is there any name for this bottle with a tube attached here?
Yes, sir. Some Bellamy.
Bellamy.
Huh?
The big.
It's called Bellamy Gardner bottle. Okay, this is a Schimmelbusch mask. So Schimmelbusch mask can be, this is the bottle that he is using. Now, can you see the difference between this bottle and this bottle? Is it visible to you, all of you?
Sir.
Yes, sir.
What is the color of this bottle?
Amber color.
Amber colored. Why it is amber colored?
Light sensitive.
It is
It
a
will oxidize to
sensitive drug.
sensitive.
It will get potency will go down if it is exposed to the ultraviolet light. So it is a light sensitive drug, so it is in amber bottle. But you have only one tube to drop that here. Whereas here, if you see, there are two tubes. What is the purpose?
Outside oxygen will
Atmospheric air will.
It is to
enter
increase the volume with air. When this air will push the drug out. Whereas in this, it will drop for a few minutes and then it will stop because the space will not be filled up. Whereas here, once the ether comes out, atmospheric air will enter in and occupy the vacuum created here and push more ether. Whereas here it will fall only intermittently. You have to allow some air to go in and again drop it. So they modified this. And this bottle is called the Bellamy Gardner bottle. Okay. So this is the actual size and the red rubber cork with the air inlet and the outlet for pouring the ether. So under what type of this anesthesia classified?
open drop method, sir.
Open drop method. Very good. What are the features of open drop method?
The patient is exposed to atmospheric pressure. There is no reservoir bag or anesthetic circuit.
The patient's airway is open to atmosphere as he breathes from the atmosphere and breathes out into the atmosphere. The volatile agent is vaporized by atmospheric air by patient's own respiration. What agents were used in this method in those days?
Ether and trilene, sir.
Ether and
Chloroform.
chloroform. Ether and chloroform.
Chloroform.
Ethyl chloride, trilene were also used. And this is the ethyl chloride bottle. Many of you had a chance to see that. Why they just a stopper with a knob like this to lever to press and all that? This is the outlet opening. It is fitted with a small cork-like thing. If you press this lever only, it will open and allow the ethyl chloride to come out. Ethyl chloride, is it a liquid or a gas?
Liquid.
It's a liquid. And it has a very low boiling point. So when you try to open this bottle, it will come out with force. It will come out with such force like a spray. And if you don't keep it closed like this, it will all evaporate in no time. Okay? So that is the reason why this was manufactured like this. So why ethyl chloride is a spray? Because it has a boiling point of 12.2 degrees centigrade, which is almost half the room temperature. So the pressure inside is twice the atmospheric pressure at room temperature. So it comes out as a spray. What are the uses of ethyl chloride spray? Most of you would not have used that. So it was used for induction of GA before open drop method because it is more sweet smelling compared to ether. And it was also used as a topical anesthesia because once you spray it on the skin, it will form ice particles. It will take up that water vapor and it will produce what is called cryoanalgesia. So we used to do incision of abscesses, incision and drainage, and the topical spray of this ethyl chloride at those days. Okay, so that's just historical. So name what is shown here.
Boils.
These are called Boyle's
Boyle's,
vaporizers for ether and trilene, which are fitted in the Boyle's machine. Boyle's bottle for ether and trilene. What are the parts of Boyle's bottle? This is just for a historical interest. So these are all the we have the so fresh gas flow will come here. If you keep it in off position down like this, all the gases will go straight without carrying any ether. But if you lift this lever, there are positions 1, 2, 3 and on. 4 positions are there. So if you keep it in on, all the gases will go into the ether bottle and then carry the ether vapor and go. But if you keep it at 1 and 2, 3, partially they will come out. So it is not very precise. So it's a rough method of separating the red gas flow, allowing it to go into that. And this is called the Epstein-McIntosh Oxford vaporizer. Okay, so this is a portable vaporizer made mainly those days for usage in World War and other field. Okay. This also used the air for its vaporization, and this bellows used to ventilate the patient. Okay, and it can be used with a mask or even microfocal tube. So it is a draw over concentration calibrated, temperature compensated by water jacket, age specific, and it's a variable bypass, the Boyle's bottle. So these descriptions you will understand better once we go into the description. So the first thing all of you have to know are the few terminologies used in physics before you understand vaporizers. So the first thing is, what is the difference between a gas and a vapor? This is a common question they will ask you in the exam. What is the difference between a gas and a vapor?
Above the critical temperature, it will emerge as a gas, and below it will vapor.
What is vapor then? Below the critical temperature. So vapor is nothing but the gaseous form of a liquid. Okay? Whereas gas will remain only as a gas. It will not be compressed into a liquid unless you use extraordinarily high pressure, because we have liquid oxygen. Oxygen is normally a gas only. But if you use extremes of pressure, then you can use on temperature, you can liquefy the oxygen also. So for major hospitals nowadays, we have the liquid oxygen plant for supply of oxygen because of the requirement and need. Whereas the word vapor is always associated with a liquid agent which evaporates and goes into the gaseous phase. That is called the vapor. Okay? And the second terminology you should know is saturated vapor pressure. What is the saturated vapor pressure? It is the pressure exerted by the vapor when it is in equilibrium with the liquid. No, any liquid which can become a vapor or which can evaporate will slowly move from the liquid phase into gaseous phase. And after a particular time, if the liquid is kept in a closed container, it cannot achieve any more gaseous form after a particular time. It will get equilibrated between the liquid form and the gaseous form. So at that time, what the pressure is exerted by the gaseous form is called the saturated vapor pressure. And what is the definition of boiling point?
When the vapor pressure becomes equal to atmospheric pressure.
Excellent. At the temperature, it is the temperature at which the vapor pressure of a liquid equals the atmospheric pressure. Okay, that is the boiling point. You should always mention the temperature of that. For example, at 100 degrees centigrade, when you boil water, the water becomes water vapor. Okay, so that temperature, before that it will not become a vapor. So only at 100 degrees Celsius, your water becomes, every day we are boiling water for our making our coffee or tea, and you would have seen at 100 degree it will start becoming a vapor, and you can see the water vapor coming out of the kettle or the vessel in which you are boiling. So the boiling point is the temperature at which the vapor pressure of a liquid equals the ambient atmospheric pressure. And formula to calculate the gas concentration in any thing is, you have to divide the vapor pressure by the ambient pressure. So the common example that's given is sevoflurane. Sevoflurane has a vapor pressure of 20.1 bar, and if you take atmospheric pressure as 100 bar, then 100 divided 2.1 divided by 100, it will become 20%. Okay, so we'll see why we cannot use sevoflurane as open drop method as we used ether the first slide. We'll see that later. What is splitting ratio? Is the ratio of breaking the fresh gas flow.
Flowing through the bypass chamber by flow
How much it goes into the vaporizing chamber and how much goes straight. It's called the splitting ratio. And variable bypass means we can alter the splitting ratio. How much I have to go into the vaporizing chamber, how much is to come straight. And measured flow is another term which we have to use for vaporizers which are not inside the breathing circuit, which inject directly the vapor into the fresh gas flow. And what is latent heat of vaporization? The word latent, what does it mean? Latent means hidden. Hidden heat. Where is the hidden heat in a vaporizer?
For the liquid to become vapor, they need a heat of.
The metal container of the vaporizer is the one which supplies the heat. Okay, that is not seen obviously. So that is why it's called latent heat of vaporization. The metal container only supplies the heat for the vaporizing chamber to evaporate that liquid. So it depends on the property of the container metal that we make out of. Whereas in desflurane, we supply the heat by a heating element. So that is very obvious. So that is not latent. That is very evident. So specific heat. What is the specific heat? This is also another physics technology. All of you would have read in the lower classes. Another terminology you have to know is thermal conductivity. So what is the difference between a gas and a liquid? Vapor is a gaseous form of a substance that is normally a liquid or solid at room temperature and then becomes a gas at a higher temperature. So what solid can become a vapor?
Camphor.
Camphor, fantastic, excellent. So gas is a substance that has no shape or volume and occupies a space above its critical temperature. Okay? And what is a saturated vapor pressure? It's a liquid contains evaporate into a small space above and the vapor pressure increases. So at equilibrium, the pressure point at which the evaporation equals the condensation, the space becomes saturated. This is called the saturated vapor pressure. Also, I have shown. Defined boiling point with the temperature at which vapor pressure equals the ambient pressure. How to calculate vapor concentrating vapor concentration using SVP and atmospheric pressure. how can you calculate the vapor concentration using the SVP and SPAC? That again, earlier I showed you to calculate the gas concentration, SVP divided by the ambient pressure. So, sevoflurane, the vapor concentration, if you use it directly onto the patient space, would be 20.1%. Splitting ratio is the bypass gas, the gas going through the vaporizing chamber. This is called the splitting ratio. Latent heat of vaporization, amount of heat needed to convert a unit mass of liquid substance into gaseous phase at a constant temperature. That is called the latent heat of vaporization. Specific heat is the quantity of heat required to raise the temperature of 1 gram of a substance by 1 degree centigrade. That is the definition of specific heat. Thermal conductivity of a material is a measure of its ability to conduct the heat. And variable bypass vaporizer. The vaporizer total background flow that enters the unit is split into two streams. And the smaller stream, which acts as a carrier gas, passes through the vaporizing chamber containing the anesthetic agent, becomes saturated with the agent. The remainder bypasses the chamber and goes into that. That is called the variable bypass, which I showed in the very first slide with the lever on the liter bottle. Nowadays, with all the tech monitors, we have the concentrating dial, which decides how much of vapor will go into the evaporating chamber. What is a measured flow? The separate independent stream of vapor carrying gas is added to the fresh flow. Example is your dust fluorine vaporizer. And some of the values of saturated vapor pressure at 20 degrees for ether, halothane, and fluorine. And you can see the dust fluorine has got the highest saturated vapor pressure of 88.5 and ether 59, all others are rest. So what will be the concentration if the agent shown here is used in open drop method at sea level?
It will be toxic to the patients.
Huh? If I have to use any of these agents as an open drop, what will be the concentration? Already we have shown you how to calculate for sevoflurane. Here is the last is the sevoflurane. What percentage you get if you use it as open drop in room pressure? I showed the calculation earlier. What will be the concentration? 21%. I did not see those things in the earlier slide.
Yes, sir.
Saturated vapor pressure divided by atmospheric pressure. 200 is that 21%.
Sir.
Okay. So like that, if you use all these things, this will be the concentration. 59% of ether, 32% ether 59, halothane 32. The same SVP will be the concentration if it is used as an open drop in the atmospheric pressure. Okay. So that is the reason why you cannot use the modern agents as a open drop method. So even though ether had a 59% SVP, it was a very safe anesthetic agent because it did not cause that much of depression of the cardiovascular system. Rather, it stimulated the cardiovascular system by stimulating the catecholamine release. Whereas all the other agents which are more potent, they will cause severe myocardial depression. They will end up in cardiac arrest if you use them as open drop technique, right? So why ether is the only agent used by open drop? Ether has a wide safety margin, that is large gap between therapeutic dose and lethal dose. So the same is average anesthetic with average skill cannot kill a patient with ether. That is the safety margin for ether. Now coming to vaporizers, how are they classified?
So, if it is
First of all,
temperature,
what is the definition of a vaporizer? Why do we need a vaporizer? Now, having seen these four, 5 slides, now you should be able to tell me why we need a vaporizer. Why cannot we use all these drugs as open drop like we used in the initial phases of our career or history of anesthesia? Why we need a vaporizer.
We can control the
Convert the liquid.
To deliver a controlled, safe concentration of the inhaled anesthetic agent. Okay, the vaporizer is nothing but a device which delivers a safe, controlled concentration of an inhaled anesthetic agent. That is the definition of vaporizer. So, how can you classify these vaporizers?
temperature compensated or not, sir.
Okay.
Plenum or draw over, and inside or outside circuit. And then
Based on output
vaporization method,
Ages.
flow over or bubble through. And another.
So, first you can say vaporization method can be flow over or injector type. This is the major classification it should be. Okay? Vaporization method, flow over means the fresh gas come inside the vaporizing chamber, just passes over the surface of the liquid. And because the liquid is constantly evaporating into a vapor, it will carry the vapor and go out through the outlet of the vaporizing chamber and join the remaining fresh gas flow and get it delivered at the outlet of the machine. Okay, that is called the flow over method. But if you want to increase the concentration, in the ether bottle, I showed you there was a plunger. Shall I go back to that and show you that?
Yes.
See, this is called the plunger, and if I just use this lever with the plunger in the pulled out position, the gases will only come over the surface and come out always. But when I want to increase the concentration, what I have to do is push the plunger into the liquid. Then the gases will go through this plunger, will bubble through into the liquid. So each bubble will have a surface area and it will carry larger vapor, and then the concentration out will be much higher than the flow over type that is going on. Okay, so that is how the flow over can be converted into the bubble through type by using the plunger to increase the concentration. And by using the wicks, again you can increase the surface area for evaporation and increase the concentration. So these bubble through and wick are all parts of the flow over technique to increase the concentration. But the injector type is one where the vaporizing chamber or the vaporizer is separate from the fresh gas flow, and the vapor is made, the liquid is made into a vapor and then added to the fresh gas flow by a separate tubing into the fresh gas line. Whereas in the flow over bubble through wick type, the fresh gas flow actually goes into the vaporizing chamber and picks up the vapor. That is the first and foremost differentiation in the classification. So flow type, flow over type, and injector type. The second concentration is regulation of output by variable bypass or measured flow. This again is the difference between the regular vaporizers that we use. Most of them use only the variable bypass, whereas the measured flow uses especially for this flow rate. Then the third is the temperature compensation, where automatic compensation can happen, or there should be supplied heat, manual thermocompensation. And your ether bottle and trialine bottle which I showed, they do not have temperature compensation at all. As the ether vaporizers, it will draw the heat from the surrounding air and through the bottle, and the surrounding air will become cooler because the heat is taken out from that. So the water vapor in the surrounding air will become condensed and it will get deposited on the bottle outside. So that is why in those days we used to say ether bottle is sweating to anesthetize the patient, because the water will condense onto the bottle surface. And the modern method of temperature compensation is using the electronic components. And the fourth classification is it can be agent specific or multiple agents. So all the tech vaporizers which we have, they are specifically made for each agent. So you cannot use the agent manufactured for halothane or say sevoflurane or isoflurane. Whereas the older method, we can, supposing ether bottle is broken, can use ether in butylene bottle and also you can use that. So there is no specificity for the particular vaporizer. And nowadays the Aladdin vaporizer which we are using that has facility for multiple agents. You can just introduce the cassette in that and start using that. And the other method is to use the plenum or draw over method. What is the plenum mean?
Because pressure
Resistance.
in the pressure in the circuit is more.
So the fresh gas flow or the carrier gas is pumped into the vaporizing chamber at a pressure, at a high pressure. Then it's called plenum vaporizer. Whereas if the gas is drawn by the patient's own inspiratory effect, then it's called the draw over vaporizer. And the vaporizer can be kept inside the circuit or outside the circuit. So most of the vaporizers that we are using in our workstation or your modern machine, where is it located? Inside or outside the circuit?
Outside the circuit.
Is outside the circuit, because after the flow meter you have the vaporizer and then only you have the breathing circuit. So it is called vaporizer outside the circuit. Whereas in olden days we used to use a portable vaporizer like Goldman vaporizer in the inspiratory limb of the closed circuit and the canister. So then it becomes vaporizer inside the circuit. And so examples based on the classification and the method of regulating output, variable bypass, you have these things. Method of vaporization is flow over and injector type, location inside the circuit, where you can use the Goldman bottle or the Oxford miniature vaporizer. Outside the circuit or the tech vaporizers. Temperature compensation, agent specific or the tech vaporizers, and multiple agent. One example is the old Goldman bottle, and also the other brand bottle, and resistance, plenum vaporizers, and draw over. So if you have to describe a vaporizer, you have to include all these 6 characteristics of that. So by saying concentration calibrated, plenum type, variable bypass, flow over with which, temperature compensated, out of circuit, agent specific. So if you include all these 6 various characteristics, then only your description of a volatile, your vaporizing chamber, vaporizer will be complete. So that is the reason why all the characteristics are given here. Now, what is the difference between boiling and evaporation? It's a very common thing that can, it's more of for knowledge. So vaporization, difference between evaporation and boiling is it is spontaneously occurring. For example, if we keep water in a bowl, look at it after 24 hours, the quantum would have reduced from what you kept. You keep it in a measuring jar and say we keep 50 ml. Next morning, if you see, it will be not 50 ml, it will be 30 ml or 40 ml. Because the slow evaporation would have reduced the quantity. That experiment all of you would have known from your school days. So it is spontaneously occurring at all temperatures at the surface of the liquid. Whereas boiling, when extra kinetic energy is added, and at only one temperature dependent on pressure, it takes place with the body of the liquid. The boiling takes place inside the body of the liquid, whereas evaporation occurs on the surface of the liquid. So what is vapor pressure? We have already defined. What is the significance? Vapor pressure predict the boiling points, create phase diagrams, and determine chemical stability. So these are all the various vapor pressures of your agents. So these are all the various vaporizers that have been used in the modern anesthesia machines. So tech vaporizers, the tech 7 vaporizers, Vapor 2000, by G, sigma, delta, all these things. And they are individually used for different agents at different times. The features of Tech 7, these are considered the latest. They are the latest model of Tech series, delivers specifically isoflurane, CO, fluorine or halothane, accommodates 225 ml. Filling capacity is 225 ml. No spill system limits, and it is filtered or inverted. And what is the purpose of the knob in this D? See this picture B shows the sigma delta penlon vaporizer. And you are seeing a knob in this here. What is the purpose of that?
For transporting.
Transporting. It is a selector tech mounting system now. Okay? Nowadays, you can use only one agent at a time and remove the other agent, so that you don't combine the vapors. So, can you identify the vaporizer shown here?
Halothane.
It is the agent specific Tech 2 type vaporizer for halothane. Okay, it is the oldest model, and you can see the dial is in the front here. Why I am showing this picture is sometimes in some hospitals and practicals, they will keep all these old vaporizers and ask you to identify just to teach you and okay. So Tech 3 vaporizer is for halothane, where the dial has gone up. Instead of the front dial, it has become top loaded dial, and you can see the Tech 3 again for isoflurane, again the dial has gone up, and the CO-fluorine, again it's called SOMNI 3 funnel fill vaporizer, isoflurane and CO-fluorine. So the methods of filling some of the modern vaporizers, they are called pour fill, key fill, and quick fill. You would have seen all these things. This is the lead cassette vaporizer where you can insert the color coded, and so that stick through all this. So Aladdin cassette is, vaporizer is asked in theory question. So you have to know all about the characteristics of this vaporizer. Not spend time because we have to go through the basics of vaporizer little more. So this is the desflurane vaporizer. This is repeatedly asked. This Tech 6 is the number of desflurane, and this is the circuit diagram. We can see this is the liquid desflurane. It is heated up by a heater here, and the vapor becomes a gas, and the liquid becomes a gas at high pressure. And then this is the flow meter which carries the gas flow. This is going down here, and the vapor is added from this to the fresh gas flow. So you can see no fresh gas flow enters the liquid chamber, and this will come out depending upon the concentration that you are taking. And some of the features of Tech 6 is again asked in the exam. So these are all the parts of that. Just sticking through all that. I cannot use isoflurane by open drop method because the saturated vapor pressure is 241 millimeters of mercury. So out of 760 ambient temperature, you will roughly have 33% of isoflurane, and that is highly toxic. It will be causing immediate cardiac arrest if you fluorine and isoflurane directly. So the function of a vaporizer is to deliver a controlled concentration, controlled safe concentration. And this picture shows the difference between the gas and vapor. So gas, however much you try to compress it, it will remain as a gas. Whereas vapor, if you compress it below the critical temperature, you can see it has become partly liquid and still vapors are present there. So that is the difference between a gas and vapor. The critical temperature is another question they ask you. The maximum temperature at which a substance can be converted from a gas to a liquid by compressing it. And the boiling point is already seen, saturated vapor pressure we have seen. The safety of modern vaporizers, the interlock isolate vaporizers which are not in use. A clear indication of the liquid level is there. A non-spill reservoir to 180 degrees allowable tilt. A key filler or a four filler system prevent filling errors and increase wick capacity. How do you calculate the volume of the liquid agent used? That is a common question they may ask you. So to calculate the volume, you can use this formula, Renworth and Eisentrapp formula. Can you tell me what is the formula?
How much fresh gas flow into 3?
Fresh gas flow percentage set dial into 3. Okay, fresh gas flow in liters per minute multiplied 3 times plus multiplied by the set dial concentration. For example, if you are using 2% CO-fluorine with a fresh gas flow of 4 liters, then 2 into 4 will be 8, so 3 will be 24. Will be the liquid use per minute if you have used. Okay, so that is how you can calculate the volume that you are using in case. And so CO-fluorine 2 liters, fresh gas flow 2 liters into 3, so 2 into 2, 4 plus, multiplied by 3, 12 ml per hour. How to calculate the amount of vapor formed from 1 ml of a volatile agent? What is the formula that you can use to calculate the vapor? So that can be Avogadro's hypothesis has to be used. So Avogadro's hypothesis says 22,400 multiplied by the density of the agent divided by the molecular weight. So for example, CO-fluorine, if you want to find out what will be the amount of vapor in 1 ml of CO-fluorine, you have to take 22,400, which is Avogadro's number, multiply it by the density of CO-fluorine is 1.53, molecular weight is 200. So if you do all the calculation, you will get 171.3 ml of vapor of CO-fluorine from 1 ml of volatile agent, liquid CO-fluorine. So each ml of liquid CO-fluorine can produce 171.3 ml of vapor. So this is called the variable bypass, where the fresh gas flow comes here, part of it goes out, the very small concentrate. This is the splitting valve which we use along with the control dial. So the control dial only controls the splitting valve. So depending upon the concentration that we set, it will allow the required amount of gas to pass into the vaporizing chamber, which will pick up the vapor and come out through the outlet. So there is an inlet for the vaporizer, the vaporizing chamber, there is a bypass circuit, and there is an outlet. These are the components of your vaporizer. And at the inlet, sometimes you may have temperature compensation to make sure that the correct gas delivery happens. And this is the injector type where the fresh gas flow comes separately and the vapor is added into that. So this is a very clear picture to show you within the flow over and the injector type of vaporization. So this is the difference between the variable bypass and flow. This picture itself very evident, so I am not wasting time on describing that. And the variable resistance controlled by the anesthetics adjusting the dial of the vaporizer, the differential pressure transducer from the, so the mechanism of this injector type is by the differential transducer which is present in that, which only decides how much vapor to be added to the fresh gas flow to get the required So these are the pictures showing the dial concentration at different settings, how much it will go. So if the dial is in zero position, as you see in this picture, all the gases go straight without going into the evaporating chamber. And by adjusting at 1, 2 level, you can see more and more gases will be going depending upon the air content. And this is the method of increasing the vaporization, either using the wicks to see, these are all the wicks to improve the surface area or increase the surface area. So more vapor will be formed and that will be increasing. Or you have to use a higher flow. Fresh flow is from the vapor in the vaporizing chamber, and this is the bubbling through as I showed in the initial thing. So fresh gas flow will go underneath the surface. Instead of the surface, it will go into the depth of the liquid column. That will cause bubbles and that will increase the vaporization. Why selection of metal with a good thermal conductivity is important in making the vaporizer? Because the temperature that is delivered to vaporize the liquid is supplied only by the container. So if the temperature goes down, the vaporization also will go down and the vapor concentration will come down. So in order to maintain that, the container has to give all this heat. And if the container gives adequate heat, then metals which retain heat will give the container. Metals which do not donate the heat, they will cause less vaporization. So that is why the thermal conductivity in selecting the material is very important. And these two things which are commonly asked, what are the effects of circuit back pressure on vaporizer output? So there are two effects which are called pumping effect and pressurizing effect. Now let me see how many of you are able to give me the answer for these two. So this is another gray area with regard to vaporizers. Students usually have some confusion over this. So can anyone describe what is the difference between these two effects of the vaporizer? Pumping effect and pressurizing effect.
Pumping effect is when the bag mask or when there is a manual ventilation, when due to pressure there is a backflow of pressure to the variable bypass chamber and the vaporizing chamber, sir. So when there's a sudden release, then the pressure gets
Very good.
That's a sudden entry into the inlet of the vaporizer and into the variable bypass, sir. So the total final output concentration gets increased, sir.
The concentration increases due to pumping effect.
Yes,
okay, very good. So she rightly said, when we do controlled ventilation, this is more pumping effect will happen more during controlled ventilation when we keep the circuit closed. And when we try to give the inspiration by squeezing the bag, the gases not only go forward towards the patient, but part of the gases will travel back towards the outlet of the vaporizing chamber. That is very important. So as I told you earlier in the picture, there is an inlet, there is a vaporizing chamber, there is an outlet, and there is a bypass bath. These are the four components of a vaporizer. Inlet going to the vaporizer, as well as the bypass path and the final outlet where the gas carrying the vapor as well as the fresh gas flow which has not entered the vaporizing chamber both mix and come out. So when you squeeze the bag, which is beyond the outlet of the vaporizing chamber, vaporizer itself, part of the bag gases will come towards the outlet of the vaporizer. And you can remember that our machines are all constant flow meters, machines. So there is a constant flow of gases from the flow meter towards the vaporizer and from the vaporizer out into the circuit. So when you do the control ventilation and squeeze the bag, part of the pressure is transferred back to the outlet of the vaporizing chamber, which pushes the onward flow coming from the flow meter through the vaporizer back into the vaporizing chamber as well as into the inlet of the vaporizing chamber. So what happens, the gases which are carrying the vapor, they are also pushed back into the inlet and they merge with the fresh gas flow and then they come through the outlet to supply more than what the dial concentration has been set. Okay, so this results in a higher percentage being delivered to the patient, which is called the pumping effect. And when they found out this, they have made what are all the mechanisms by which you can avoid this pumping effect. Whoever answered that, can you continue with your answer? What are all the methods of avoiding this pumping effect which can deliver a higher concentration than the concentration set by the dial?
By increasing the resistance.
Resistance to or preventing the back pressure or backflow of the gases. You can incorporate a valve there, or you can increase the length of the inlet tube so that the backward flow of the gases containing the vapor do not merge with the fresh gas flow at the inlet. Okay, so these are the two mechanisms by which you can do. So I will change all these things. So during generating a positive pressure, the bag is squeezed, pressure in the breathing system increases, and the pressure is transmitted back in both the bypass channel as well as the vaporizing chamber. The fresh gas tries to move forward but gets compressed both in these locations. And during sudden release, what happens? The positive pressure expiration is released. So the previously compressed gases now suddenly expand in all directions. Some of them rapidly expand, containing the vapor, and enter the inlet of the vaporizer and cross over into the bypass channel. This is how the concentration is increased. So the gases go in the reverse direction towards the inlet of the chamber and then increase the concentration. And the final output concentration will be so bypass will be the flow across the bypass will be there. I'll show the pictures of this nicely. The bag is squeezed, producing a back pressure effect. Now you can see the bag is squeezed and the pressure is going out both towards the bypass chamber as well as into the vaporizing chamber. Okay, but the fresh gas flow is continuing to come in this direction. Okay, and the blue dots are the fresh gas and the pink dots are the vapors. Now here what happens? Again the bag is squeezed, the vaporizing chamber is so it is pushing all that gases back into that, and so much of gas is being kept here, and this gas which has entered here, you can see the direction of the arrow. Here it is coming here, and part of it is being pushed out, and you can see the fresh gas flow. Blue dots are now replaced with the vapor. All of them are trying to go towards the inlet, and some of them enter the inlet and then join. Actually, this arrow shows that the vapor which has been pushed towards the inlet has joined with bypass gas, and it is coming out and it is increasing the outlet. So you can see the concentration is actually increasing. So there is a higher output. The bag is released. So this is what is called the pumping effect. The methods of reducing the pumping effect are: you can have a long inlet tube so that the gases which are coming out will not enter the bypass chamber, or increase the resistance in the outlet, or you can put a one-way valve. So the valve will block the back pressure coming here completely. So when you squeeze the bag, the valve will close any backward flow, and when you relax the bag, it will open up. So three methods for reducing the pumping effect. One is having a long inlet tube, The second is to cause a resistance at the outlet. Third is to put a one-way valve in the outlet. So by these three methods, you can reduce the pumping effect and thereby prevent the abnormal increase in the concentration that is being delivered. Now the pressurizing effect is again a part of this back pressure effect, where the species but it is due to the compression of the fresh gas in the inside the vaporizing chamber only during high fresh gas flow. So that is the difference between the pumping effect, where the pressure is reflected both to the bypass chamber as well as the bypass pathway as well as vaporizing chamber. But the pressurizing effect is mainly because of a high fresh gas flow, increasing the pressure in the vaporizing chamber alone. But ultimately, what happens, even though the pressure is increased, when the bag is released, the concentration of the vapor in the mixture will be the same. And so the fresh gas, which is coming after the pumping effect, after the pressurizing effect, by the increase in the vaporizing chamber, somehow lowers the concentration rather than increasing the concentration. So pumping effect results in increasing the concentration, whereas pressurizing effect lowers the concentration because the pressure is mainly transmitted only into the vaporizing chamber and only when you use a high gas flow rate. And pressurizing effect, strictly speaking, is not a very important issue in inhalation anesthesia unless you use very high flow rates in closed circuit also. So that is the reason why nowadays we are going in for the low flow anesthesia technique, where the total flow is reduced to as low as less than 1 liters. And in the olden days, when they used to use 3 and 6 or 2 and 4 for closed circuit itself without adjusting pressure limiting valve in a partially open position, this pressurizing effect had a particular say. But nowadays with the low flow, this pressurizing effect is negligible. So you can just remember that pumping effect definitely increases the output concentration, whereas pressurizing effect lowers the concentration only when high flow rates are used. So that's all what you have to remember for these two particular phenomena. Now, if you read check flow rate, what are the safety features of that has been incorporated in the modern anesthesia machine? They are color coded. Their key fill bottles are there. Low filling port, secured vaporizer interlocks are there. Only one vaporizer is turned on at one time, and gas enters only one which is on. The trace vapor output is minimized when the vaporizer is shut off. Vaporizers are locked into gas circuit and ensuring they are seated correctly. And concentration dial increases output when all the rotated are clockwise. So hazards of vaporizer, there are a lot of hazards: misfilling, contamination, underfilling, fitting, overfilling, and leaks. And this is the interlocking system. All of you will be aware. The methods of filling to be shown, to key filling and pore filling and QC filling, all these things. And the name of the agent specific pin safety system that is used for that is called Fraser Sweatband pin safety system. The components of this system are key bottle collar, adapter tube, vaporizer filler receptacle. So this will be filling only when vaporizer is off position. So only vaporizer which can be filled during on position also is which vaporizer?
That's fluorine.
That's fluorine. Fantastic. So all others you have to switch off the vaporizer, otherwise there will be a cat leak. Name of the mechanism. Dalton's law. Percent. What is volume percent of the number of units of volume of a gas in relation to total of 100 units volume is called the total gas mixture. So volume occupied by gas by total volume multiplied by 100 will give the gas percentage, which we saw in the earlier slide also. So plenum vaporizer means the full conditioning. The technology applies to air that is forced in and cleaned and temperature adjusted. So plenum vaporizers are designed for use with continuous flow pressurized gas. And this is the world's first precision vaporizer, more immediate proof with the side filling port, including overdose. This is called the copper kettle vaporizer. So these are all now become specimen. So it is more like a less fluorine. It's something like a copper kettle only, because the flow meters are separate and the vapor added to the flow separately. The difference between Tech 2 and Tech 3, sometimes they ask you, not going into the details. Tech 4 vaporizers and their features, and Tech 5. Each one has got their own features. These are all the different models for the student vaporizer you can use. Tech 6, Drager and Penlon. And methods of temperature compensation. This is another point you have to remember. So it can be metal rod temperature compensating value. So you can see this is the single rod with a top which is expanded. So depending upon the temperature is low, it allows less of the fresh gas to come in and take up the vapor. And when the temperature becomes high, it will try to, when the temperature is high, rather this is showing high temperature, it tries to occlude the fresh gas inlet to reduce because heat will make more vapor to form. So to avoid excessive vapor being formed, it reduces the fresh gas inlet and allows the same concentration to be maintained. When the temperature gets dropped, it will allow more fresh gas to come in and pick up more vapor to again maintain the same concentration as the diaphragm. So that is the metal rod method of temperature compensation. Then there are liquid bellows, so which again, when the temperature increases, they all expand and try to reduce the inlet of the fresh gas. And when the temperature drops, they shrink or they reduce in size and open up to allow more fresh gas flow. So the ultimate point that you have to remember is, if the temperature increases, then fresh gas flow into the chamber should be reduced. When the temperature decreases, more fresh gas flow should be allowed to come into the chamber to pick up more vapor. That is all the concept. So that is achieved by various methods like this metal rod, liquid bellows, or the bimetallic spring. This is called the bimetallic spring, where you have two metals of different specific heats, and they will try to be straight or bent on one way or other, try to adjust that. So you can see this is how when the temperature is high, they try to include the inlet port, and when the temperature is low, they bend the opposite direction to open up the fresh gas flow inlet. So all the methods are the same. So metal rod, liquid bellows, or bimetallic strip, which all try to adjust the fresh gas flow inlet into the vaporizing chamber. So these are all the various Aladdin cassettes which are also there, how to use that. This is a comparison chart between all the various vaporizers. And the newer method of vaporization called direct injection of volatile anesthetic agent, which is called DIVA. So it uses a measured flow vaporizer, but can be used for all modern anesthetic agents, including the fluorine. It has two sections: a plug-in vaporizing module, which is specific for a particular agent, and another part of a anesthesia machine. So it has a storage liquid from tank, entering third evaporation chamber and patient circuit. So this is produced by called Maxwell. So I just included this because being a newer invention, then we suddenly ask a short note question on that. So you can just read about that. And hazards again, dealing with this fitting, overfilling, underfilling, leak, etc. Electron failure, contamination, reverse flow, etc. And another one newer thing is the anaconda, which is asked in short notes from the earlier theory papers. So where is it used, this anaconda vaporizer?
ICU, sir.
ICU sedation on for ventilated patients. Okay. So just saying ICU is not the answer. You should say it is used for
Ventilated.
sedating patients on ventilator instead of using muscle relaxant and propofol for sedating the patient. You can use this, which is easily eliminated and recovery will be faster. So this is the thing that is being used. It is nothing but a miniature HME, anesthetic vaporizer and a HME combined together. So the device is meant to be used mainly for sedation in intensive care unit and outside operating room, designated to deliver only isoflurane or sevoflurane, available presently in two different internal volumes of 100 ml and 50 ml to be used in patients with high and low tidal volumes. So that is all the things about vaporizers. So any doubts or any questions on that?
Sir, ether and ethyl ether, diethyl ether, all different inhalation also.
Ether is also called diethyl ether. Ether and diethyl ether are same. And all the modern anesthetic agents nowadays, what we use as halothane, desflurane, isoflurane, fluorine, all are halogenated ethers. So they are all derivative basically from ether only, created from ether. With the addition of halogens, some of them had hydrogen, some of them had chlorine, some of them had bromine. So they are called halogenated hydrocarbons. They are the offshoot from ether only. But the basic difference is ether had an analgesic property along with anesthetic property. But the offshoots or the modern agents of ether, they do not have analgesia. They produce only unconsciousness, but they are not having any analgesic property. That is why we have to give supplemental analgesic also. Whereas in the olden days when we were using ether, we used to give very minimal analgesic because ether itself had a good analgesic property. So we can do small, short duration surgeries with ether alone without giving any other narcotic or analgesic agents. Any other questions?
No, sir.
No, sir.
Okay. So I hope able to clear your doubts or make it as understandable as possible to the best of my efforts. You still have doubts, so just make a note of it and try to ask later. I will try to clarify.
Yes, sir.
Yes, sir.
Yes, sir.
Kamachi,
Yes, sir.
shall we close?
Yes, sir. Thank you very much, sir. Can
Thank you,
we
sir.
Thank you,
sign
sir.
up to the class, sir?
Thank you, sir.
Thank you very much.
Good night, sir.
Thank you, sir. Good night, sir.